Okay, hello everyone. Hopefully you can hear me okay. Um, so by now you should have looked at the two videos on part 1 of section 3.1, and now I'm going to do the remainder of section 3.1, which will be the notes for Friday's class. And at the top here, I sort of put the homework problems. These are the homework problems for Friday that you'll be working on in class. You'll be working in the same groups that you worked with on Wednesday. And so you'll just be continuing with that group, and then next week it'll be a new group. Okay? All right. So this heading, and I also, if you printed off the first packet, I changed this one a little bit, the remainder of it, because I needed extra pages. I didn't gauge how much space I would need. And so I'm going to upload the new packet with the extra spaces, or you can just use blank paper or however you're doing it to put in the extra spaces. Okay? All right, let's get started because hopefully this will just be one video. Okay, and again, if you want to stop the video and write everything down and then play it so you can go through everything with me, that's fine. All right, so we talked about the linearity principle in the first video, so I won't go back over that, but just keep in mind we can extend it to any solution to make more solutions, and we do that because once we know two solutions, call them y1 and y2 of our system, then we can create a linear combination by adding constants k1 and k2, and we can write a linear combination. And so we have here, notice k1 and k2 are our parameters, correct? So we have a two parameter, we call this a two parameter family of solutions, okay? And so now let's bring in initial value. So let's say we have an initial condition and we want to find the solution to the system with the given initial condition. And so in this example, so again, we're going to use the same constant coefficient matrix A that we used in the last example in the last slides. And now we want to find a solution with this system where y of 0 is equal to 2, the vector 2, negative 3. Okay. Well, what do we know? We know that we have these two solutions already. Those were given to us in the last example. And so if we let's evaluate those two solutions at 0. Because if one of those solutions give us 2, negative 3, then we're done, right? Because of existence and uniqueness theorem, which we're assuming here and we may get into a little later in the sections. But so y1 of 0, so we're plugging in 0, and I'm going to leave it to you just to save space, but this is really, it's e to the 2t, right? So e to the 0 is 1, and so that's how y1 of 0 is 1, 0, and y2 of 0 is negative 1, 2, and so you can make sure you check that, make sure you agree with that. And so since either of those gave us the 2, negative 3 that we looked for, those are not solutions to the, that's what that said. Hopefully you can read my writing too because the stylus sucks. But anyways, those are not solutions to the IVP. So in other words, what we need another solution, let's call that y sub 3 of t, such that y sub 3 of 0 is equal to 2, the vector 2, negative 3. Okay, well, we know we can find that because we can take the two solutions we know and take two of our parameters, k1 and k2, our constants k1 and k2. And so what we desire is a y sub 3 of 0, which is equal to k1 times y sub 1 of 0 plus k2 times y2 of 0. And in the end, we want that to give us 2, negative 3. And hopefully, again, if this isn't making sense, go back over sort of linear combinations, because all I'm saying is that y sub 3 is going to be a linear combination because all the solution, once you know two of your solutions, all your solutions will be a linear combination. It's a special condition, actually, once we'll talk about in a minute. Linear independence has to hold. But once you know that, then you can make that combination, okay? So now this is just right here. This is just a matter of algebra, okay? So in this next slide, well, so from here, this is y sub 1 of 0 and y sub 2 of 0, right? And so we already found those values. We know y sub 1 of 0 is 1, 0, and y sub 2 of 0 is negative 1, 2. So if we substitute those in, that's all we did was substitute those in here and then distribute across. And I think in the last video I showed you how to do that. So this now becomes a vector k1, 0, and this becomes negative k2, 2, k2. equals 2, -3. And now we have a system of equations because remember we can add straight across. So this becomes K1 minus K2 equals 2 and 2K2 equals -3. Okay. And I want you to hopefully you can go back and check. So I simplify showing all the steps. So make sure, and I do that throughout the video to save space on the slides, but I want to make sure you guys in your notes should have it finished completely and check my answers because I could be wrong, so let me know. And so K1 and K2, if I did my arithmetic and algebra correct, K1 is 1/2 and K2 is -3/2. And that's telling us those are the constants that's needed to give us what we're desiring. And so then that tells us then that y sub 3 of t, so the solution, the particular solution, is equal to 1/2 times y sub 1 of t minus 3/2 times y sub 2 of t. And again, I'm going to leave it to you to simplify, but this should be your final answer. So we just found a solution to our initial value problem. Isn't that cool? I love vectors. I do. It makes our life a lot easier, I think. And you can check to make sure if you plug in 0 here, you should get out to -3. Okay? And what you will, because this will be, this up here is going to be 4/2, which is 2, and this right here is going to be -3. So yeah, it works. Okay? Let's move on. So now let's look at linear independence, okay, and see what we mean by that. All right, so linear independence. So recall back here when we had our two vectors. So recall that y1 of 0 gave us the vector 1, 0, and y2 of 0 gave us the vector -1, 2. Okay? All right, and if we look at vectors, and if you don't know how to graph vectors, just in terms of keeping it simple, think of this as, so so for vector 1, 0, you go to the point 1, 0 on the plane, and you create a vector. So you go from the origin to your point, and you take the direction of that. So since from the origin to that point, we're going to the right, that's why it's a vector arrow pointing to the right. And then from, so this is, and I'm writing it in this form just to save space, but this is vector 1, 2. And then we had negative, that should be a negative, we had -1, 2. I'll do a different color. Okay, then we had -1, 2, which is here. And that vector coming from the origin is about here. So this is vector -1, 2. Okay. And so my little note over here tells us, so what this is saying, what my note is saying is that vectors not on the same line, I forgot to put line there. Isn't surprises nice? Surprises are nice. Vectors not on the same line through the origin are what we call linear independent. So these are just different ways to think of linear independence. If two vectors are not on the same line through the origin, they're linear independent. And that means, so that's why I put the equal sign there, that vectors can be written as a linear combination of another vector. So that condition has to be met. So if you have two solutions like we found, and we just showed that their vectors here, y sub 1 of 0, y sub 2 of 0, their vectors through the origin are do not go through the same line, therefore they're linear independent, and thus we can write it as a linear combination, which we just showed here, and that's how we came up with y sub 3 of t. Okay. Another way, probably a more simpler way to say that, is that when you have two vectors, if they're not multiples of each other, they're linearly, we could say linearly independent. And again, this is, we're keeping it simple because we're talking about a 2x2 matrix, so our vectors are in 2-dimensional. If it gets in further dimensions, for those that has taken linear algebra, you know certain other conditions have to be met, because it may not be as easy to see if the vectors are multiples of each other. But since we're, for the most part, just going to be dealing with 2x2 matrices and vectors in 2D space, then we just need to remember these properties. Okay, and from that comes a theorem that tells us if x1, so, and these are vectors, so if you want to put an arrow above that to let yourself know that these are vectors and not just points, but actual vectors, which means direction. So if x1, y1, and x2, y2 are linearly independent, I'm using my shorthand, notation here, vectors. Then for any x naught, y naught, and for those who haven't had foundation, this means there exists, guys are getting ahead of the game. So there exists K1 and K2, and this means such that, I don't have room to write it, but that means such that K1 times vector x1, y1 plus K2 times vector x2, y2 equals x0, y0. All this is saying is what we just proved in this example. That's what we showed in this example, okay? So don't get too intimidated with all the letters. That's what we just showed in that example. All right, so now let's think about the general solution, okay? And so again, let y1 know, given that y1 and y2 are solutions to our differential model, and in this case, again, we can look at it as vectors and matrix with the matrix A. If y sub 1 of 0 and y sub 2 of 0 are linearly independent, then for any y of 0, this is y of 0 equals x sub naught, excuse me, comma y sub naught, we can find constants or parameters k1 and k2 such that k1 times y1 of t plus k2 times y2 of t is the solution to the initial value problem given some x sub naught, y sub naught. And they actually showed you in the book in general. I'll leave that to you. You should still read the book in its entirety. I'm just sort of pulling out some of the main things I want you to make sure you understand. And so once you find that, that's your general solution to your system, okay? And just a couple notes on that. So by the existence and uniqueness theorem, each initial value problem for a linear system has exactly one solution, okay? So that's nice. So that's why from the beginning when I said if we were to plug in y, so 1 of 0 into, I'm going back just to emphasize. So yeah, if we were to plug it in here, so if for instance 2, -3 came out here, then we would have been done, so, because we would have known that y sub 1 of t is the only solution for that initial value problem. Okay, so that's all that. That's by the existence and uniqueness theorem. And we now know how to find all y sub 1 and y sub 2, where y sub 1 of 0 and y sub 2 of 0 are linearly independent, and this is called the linearly independent solution. Okay. The last thing, so we're almost done. The last thing deals with the undamped. So we're coming back to our undamped harmonic system that we talked about on Monday. All right, and so recall from section 2.1 or what the example we did in class, so you can look back over your notes of what we did in class. We were given this second order differential equation, and we found in class that y sub 1 of t cosine equals cosine t was a solution. I believe someone in the class said that sine of t was a solution, and we said it wasn't, or I can't remember, something along those lines, but it actually is, and you can check that too to make sure. But it actually is. If you take the prime of this and the double prime of it, it actually, the left hand side here equals the right hand side. So it actually is a solution. So we have two solutions, okay, for that second order differential equation model. Say that 3 times fast. And remember, we turned it into a first order system, right? So we turned it into that first order system, which you should know. If you're given a second order system, you should know how to turn it into a first order system now. And well, from the undamped harmonic oscillator equation, right? All right, and so just keep in mind, so if we change this in terms of look at it as a vector, then we can say the vector y of t is equal to y of t v of t, okay? And dy over dt equals. So here's the thing, because I know you're like, where did this come from? So I'm taking this first order system. So when we convert it to a matrix and a vector when we convert it to sort of a matrix vector system, we use the first order system to do that, okay? You'll see we'll come back to that second order in the end, and actually we're going to answer the question, because again, someone asked this, which is a good question, right? Like, what are we doing this for, right? We're doing this to find y. We're trying to find y, which is a function, right? So we're trying to find our function y. And so it's easier sometimes to take a second order system and turn it into a first order system to find that y. And so once we have our first order system, then we take that first order system and turn it into, we can look at it with matrices and vectors, and that can help us simplify our life as well. Okay, so it's sort of this trickle down effect. Okay, and so dy over dt, how did I get this matrix A? How did I get this matrix A? Well, remember that if y of t vector is y of t and v of t, then dy over dt, this is really, remember, I talked about this I think in the first video, dy over dt and dv over dt. Hope you guys can see that, okay? Well, looking at dy over dt, and so we're correlating it to this row, there's no, so the first entries represent our y of t coefficients, and the second entry represents our v of t coefficients. So in this first row, looking at dy of dt, there's no y, right? It's just v, right? So that's how we got that 0 there. And then there is the coefficient in front of the v is 1, and that's how we got that 1, okay? And now here we do the same process, and I'm going to erase this in a minute because it's looking sloppy, but just to emphasize. So we look at this row, and the coefficient is -1. That's how we get that -1, and there's no v, and that's how we got that 0. So that's how we created our constant coefficient matrix. All right, A. And then we have, of course, y. And of course, if you multiply that through, you will get back that system right there. Okay. All right. So now let's see what we have. So we have y. We know y of t equals the vector y of t, v of t. We also know, so it's important to keep in mind that v of t is the derivative of y, right? Because it's a velocity, so it's the derivative of y. Well then, y1 of t is, we can write that as y sub 1 of t, v sub 1 of t, and we said the solution to y sub 1 of t was cosine t. Well, if v is the derivative of y, then we just write that as the cosine, the derivative of cosine, which is negative sine t. That's how we got that. And similarly, y2 of t, y sub 2 of t, we said another solution was sine of t, and the derivative of sine of t is just cosine of t. And so that's how we got that column vector, okay? And so then we can plug in, so let's make sure, we want to make sure that y sub 1 of 0 and y sub 2 of 0 are linearly independent, because once we show that, then we have the general solution to our differential equation model, okay? So y1 of 0, and just plug it in. I didn't have time, but that's cosine of 0 is 1, and negative sine of 0 is 0, so that's how we got that vector. And then for y2 of 0, sine of 0 is 0, and then cosine of 0 is 1, and that's how we got that vector. And if we graph, I already graphed it for you guys, if we graph the vectors to those, we see that they do not go through the same line. You could also just look at them. If you had linear, these two vectors should look familiar, and if not, you can just look to see they're not multiples of each other, or you can graph it to make sure that they don't go through the same line. So that tells us we have the general solution. So thus, the general solution to our model is y of t equals k sub 1 of t times y sub 1 of t plus k sub 2 of t times y sub 2 of t, which, if we put in those values, equals that. Now, here's the thing that's interesting. Remember, at the end of the day, what are we trying to answer? We're trying to find y, right? It's little y. We're trying to find our function, all right? And just keep in mind, y of t, this vector, so big Y, this vector, it composed of two functions, y of t and v of t. Our concern was only y. So now this is because, again, we started off with the second order differential equation, right? And that was just in terms of y. V wasn't involved in that. And we're just trying to find y. So therefore, all we need to take is our y portion of this vector in our solution here, which is just this first row. And so if we take that, we have our solution. So our solution, so our y of t is equal to k sub 1 of cosine of t plus case of 2 times sine of t. Okay, in future chapters we're going to learn how to sort of condense going through all this to find this general solution, but for now it's still much easier to do it. Vectors help us figure out our general solution. Okay, so hopefully this made sense. I'm done, and we are done with section 3.1.